Okay, now we're at the second video, where I will be solving the question 6, C and D sub-questions. And at first, I will be solving the question 5's last sub-question because apparently I forgot that. Okay, the question 5 was asking us at C. Let me check. We will be using a different seed number for X0. So it says change X0 to your student ID to get a new stream of 10,000 pseudo-random numbers. Okay, now we're at question 5C. We have the same A value, same C value, same M value, and now I will be changing this to my student ID. Okay. So depending on the seed number, obviously, we will be having a different sequence. So different seeds produce different sequences. And so these differences make sure that we have different outcomes in the simulation. So these parameters, the seed, C, A, and M are very important for these sequences because we want a long cycle length, maximum as possible, and uniform, conform to the properties of, uniformity and independency. Okay, so that was this. Let me go to the question 6. So on exercise that's 4, question 6, let's check it. It says, so I will be solving the sub-questions C and D. It's about the Kolmogorov-Smirnov test, and we will be using Microsoft Excel again and test, check if the random number is generated by linear regression method. Okay, so Kolmogorov-Smirnov test compares the difference between the CDF of a standard uniform distribution fx and the empirical CDF Sx of a random number sequence. I again suggest you to watch the Asynchronous theoretical lecture video about this. So these frequency tests are performed to check the uniformity property of a random sample. You can either use Kolmogorov-Smirnov test or the chi-square test. So they both measure the degree of agreement between the empirical distribution of a sample of generated random number and the theoretical uniform distribution. So Kolmogorov-Smirnov test can be used for any sample size, but it requires more computational computation, but it's stronger than chi-square test. So you can use chi-square test for sample sizes smaller than 50 as well. I'm sorry, using this for sample sizes smaller than 50 is not recommended. However, you can use Kolmogorov-Smirnov test for any sample size. However, chi-square test is has less computational complexity, so it's easier to use. Okay. Now back to Kolmogorov-Smirnov test. Again, we are comparing the difference between CDF of a standard uniform distribution and the empirical CDF of a random number sequence. Okay. So the CDF of a standard uniform distribution fx equals to x. So it's equals to a certain number, and this x is between 0 and 1, and the empirical CDF equals the number of these random numbers, which are less than or equal to x over the sample size n. And okay, let me start. So it says generate n equals 500 random numbers using LCM, linear congruential method with parameters. Okay, it's the same with the 5C, right? So I don't have to change it to my student number. It should stay as like this. Was it 22? Okay, let me add another 2 here. Okay, this was the original one. So it says implement the Kolmogorov-Smirnov test and calculate D. For alpha equals, so I will be explaining that. 0.01, conclude if the sample is really uniformly distributed or not. Okay, since we are checking the difference between those CDFs, again, I suggest you to go to LMS and check these comparison between theoretical CDF and empirical CDF graph. And so we will be looking for the maximal difference between theoretical and empirical lines and choose the maximum absolute deviation. Okay. So our algorithm goes like this. We rank the sample from smallest to largest, the random numbers. So our Ri is the ith smallest observation. And at the second step, okay, let me go here. At the second step, we are choosing two values. So it goes like this. Okay. We are choosing a theoretical upper bound and a theoretical lower bound. So which they will be like D plus and D minus. So we will be computing the test statistic. And to compute that, we will be using these formulas here. So to use those formulas, we have to compute I over N and then I over N minus Ri. So if you have those parentheses on R, it means the observation in the sequence. If there is no parenthesis on the R like this, Ri or Ri, those are two different things. This is the unordered one. This is the observation in the sequence, ordered sequence. Okay, so after finding those D plus and D minus values, we compute the test statistic D, which is, like, let me write like this, the maximum of D plus is like this, okay? Okay, between these two values, we are achieving the maximum one. So this test statistic equals to the maximum deviation between the theoretical and empirical CDF. So at the fourth step, we will be locating the critical value, the alpha in table, Kolmogorov-Smirnov critical values for n for our specified significant level. In the question, what is it? Let me check. It is 0.01. Okay, let's write this like this. I'm pretty sure it's written down the table, but okay. So if D is greater than the critical value, we will be rejecting the null hypothesis. So we will be saying that the random number sample does not follow the uniform distribution, and if D is smaller or equal to the critical value in the table, we will conclude that there's no evidence to reject the null hypothesis. So we will be failing to reject. So the random number sample may come from a standard uniform distribution. So we will be having two cases there. And for every hypothesis, we actually start with stating the null and alternative hypothesis. Let me write it like this. It looks ugly. Okay. Let's write null hypothesis. And this is the alternative hypothesis. So, okay, we can write like this, Ri, I couldn't find the sign, so, okay. It follows the uniform distribution. It comes from a sample of, what have you said? Standard uniform distribution or otherwise here. Okay, so at the end of the test, we will be deciding on this. So at first, we are computing these values, right? So this is the order sequence. As you can see, it goes from the smallest to the largest. And we found these values on question 5. So we actually ordered these values for question 6. So from smallest to the largest, it goes in increment. We have this Ri column. And again, it has parentheses, so it has the observation in the sequence. Now here we are computing the I over m value, and I is our, like in this column, 1, 2, 3, 4, it goes on like this. It's like the iteration. And n is the sample size. So what was our sample size? It was, I think, 500. Let me check. Yes, it's 500 random numbers. So we are dividing this A2 value, which is 1, I value over 500 for every cells, and we propagate it down after writing this for the top of the cell. So after computing I over n, we are computing I over n minus Ri. So we are subtracting this Ri value from this I over n value. Okay, so the maximum of this value will be our d plus, and the maximum of this value, which we will be computing right now. Okay, let's check. It is the reverse computation. We will be subtracting this time I minus 1 over n from Ri. So we have those numbers, and let me remind you, we will be finding the max positive value here. So we are not looking for the absolute values. So if it's negative, then it's absolutely smaller than a positive value. So out of these values, we are finding the maximum positive value, the maximum value. And out of here, again, we are finding the maximum positive value. So this column computes here, the maximum of this, the theoretical upper bound, and this column computes, the maximum of this column computes the theoretical lower bound. So we will be finding the maximum deviation of our theoretical CDF from the empirical CDF. So out of this, the value we found from here and from here, again, we will be choosing the maximum out of these. So we wrote those formulas, propagated down, and let me go to the end of this table. So after 500 iterations, we generated 500 random numbers. So we use linear congruency method, right? So we are trying to check the uniformity property of this random sample using Kolmogorov minimal test. Okay, here with the formula maximum, we are finding the maximum value of this column, and again using the same formula, we are using the maximum value in this column. So out of these values, what is the maximum? It is this value, which is 0.0306, and it goes on like this. And we are actually finding this critical value from the table, Kolmogorov minimum critical values table. And we will be looking up for the 0.01 value, right? Yes. So on this table, if you can check the Kolmogorov minimum critical values for degrees of freedom. Okay, let me write also here this. In Kolmogorov minimum test, our degrees of freedom is n, which is the sample size. It is 500. For degree of freedom 500, we are looking for the D, which has the significance level of 0.01. So when I check the table, okay, so on the table, we have values up for degrees of freedom up to 35. So after over 35, we are actually given 3 different formulas for different significance levels. So if the significance level is, I can also write that. If it's like 0.10 for 0.5 or 0.01, we have different formulas. For this over, let me write like this, over 35, the formula is 1.22 over square root of n. For significance level of 0.5, it is 1.36 over square root of n. And for this 0.01 is 1.3070, what am I saying? 63 over square root of n. Okay. So according to that, we are computing this okay, d of a value. Okay. So we are applying this formula because our significance level is 0.01 and our formula is 1.63 over square root of 500, which is written in the formula. So as you can see, it is larger than D, which is our test statistic. So if test statistic is larger than critical value. Okay, let me off here. It looks ugly. So we have two cases. We reject null hypothesis, which was the random number sample does not follow the uniform distribution. But this is not our case, obviously. If is smaller or equal to the alpha, we fail to reject the null hypothesis. Okay. So we are in this case, right? So what does failing to reject the null hypothesis mean? We conclude that there is no evidence to reject the null hypothesis. So the random number sample may fairly come from a standard uniform distribution. Okay. So what does the question ask is, okay, let me check again. Implement the Kolmogorov-Smirnov test and calculate D for the significant level. Conclude if the sample is really uniformly distributed or not. So we conclude it may come from a standard uniform distribution. So on sub-question D, it says, if we were to draw the empirical CDF as X of the sample in C, what would it look like? So again, I am asking you, actually, not suggesting, you to look up for the graph of the comparison between the CDF of standard uniform distribution and the empirical CDF, which are Fx and Sx. On the x-axis, we have the random numbers, and on the y-axis, we have cumulative probability. For if you look at that, at our first observation from the source sequence, we are jumping to the certain values, and we from the graph actually we are seeing how much we are deviating from how much the empirical CDF values are deviating from the theoretical CDF values. So in our case, in this question, since we are failing to reject, so it may come from this generated random numbers come from a standard uniform distribution, we can say that it will be a staircase function that closely approximates CDF fx in the unit interval 0, 1. So if you were in the class, I will be drawing that. But right now, I cannot connect my iPad to computer. So if you don't understand this question from the solution set or the slides, please come to my or SNS office hour. So in the next question, in the next video, I will be solving the question 11. No, 7. Okay.